Hi everyone, my name is Vijay Narasimhan and I am the manager for incubator programs at EMD Performance Materials. And today I'm going to be talking about some collaborative work that happened between EMD Performance Materials thin films and the team at Intermolecular on investigating the inherently ferroelectric behavior of films grown by ALD from ZrD-04 and HfD-04. So to give you some context about this, we're going to divide the presentation into three spots. So first, we're going to talk about the background of this field of ferroelectrics using hafnium and zirconium oxide. And then I'm going to talk about some of the base properties of hafnium and zirconium oxide films grown using HfD-04 and ZrD-04. And finally, I'm going to talk about the ferroelectric testing that we did on films that were combined hafnium zirconium oxide films. So starting with the background, let's do a quick introduction to ferroelectrics. So the simplest way to think about ferroelectric materials is that they are non-linear capacitors. And so a capacitor conceptually is an insulator or a gap that separates two conductors, in this case, two metal electrodes. And then we apply a voltage across this structure, and then what we get is a separation of charge across the insulator. So there's a couple of different ways that charge can separate. So either the electron cloud around individual atoms can be displaced slightly, or you can actually have atoms that move place entirely, therefore causing a change in the distribution of where the positive and negative charges are in the material. So the key aspect of a ferroelectric is that there is an apparent stored charge in this material. So overall, the material still looks like it's neutral. It still has the same number of positive and negative charges. But when you take the voltage away, unlike the case of, say, a polarized atom where the electrons would just slosh back to the center again, the charge stays apparent on the material. And so that separation of charge that you induced by applying voltage remains. If you plot that on something called the polarization versus voltage or electric field plot, what you will get is hysteresis. So as we sweep up, we increase voltage, we achieve some polarization state, and when we sweep back down, instead of that polarization going away, we're left with some remnant polarization, and that quantity is called remnant polarization PR. So there are lots of potential uses for ferroelectrics for different applications in computing. And so one of them is using ferroelectric tunnel junctions. So this is that metal insulator metal structure that we showed before. And basically, by switching the polarization state of the ferroelectric, you're able to change the resistance across this junction between two metals. And this change in resistance corresponds to a change in the state of a bit between a 1 and a 0. You also could actually apply this to multi-level switching. So instead of just between two states, 1 and 0, you could have multiple states in between. This is what's demonstrated in the lower figure here in a recent picture by Kioxia. And that could be really useful for applications like neuromorphic computing when you actually need computing elements that simulate more closely analog behavior. These types of materials could also be useful for logic. And so here we have something called a negative capacitance transistor. This looks a lot like a standard MOSFET, but in addition to the oxide that's in between the gate and the channel material, we put this ferroelectric material in place as well. And because of this large nonlinear capacitance, as we apply voltage to our gate to turn our channel on and off in two states in a logic material, we can actually get a subthreshold slope, which is much faster than what can be achieved in a normal dielectric material. And so this could have big impacts for power consumption in this type of device. So all kinds of useful applications for these materials, as long as we can find the right ones that could be integrated into standard CMOS semiconductor processes. So that's where we come to these exciting hafnium oxide-based ferroelectrics. So this behavior was discovered in 2011 in this fundamental paper in Applied Physics Letters. And basically what they found in that paper is that you could actually, in a material that's been known and been used in capacitors for both transistors and memory devices in computing for years, if you are able to induce very specific growth conditions, you can actually get that material to be ferroelectric. And so here what we see is a combined hafnium oxide zirconium oxide layer that's sandwiched in between two titanium nitride electrodes. And then when we look at a very similar structure that we actually studied at Intermolecular, you can indeed see that you have this hysteresis behavior like what we observed in the theoretical version of what a ferroelectric would look like. And the great thing about these materials is that the CMOS integration is much more easy than the traditional ferroelectrics like lead zirconium titanate. And so the key as to why the deposition conditions need to be specific and why we've been investigating these materials for years but didn't discover the ferroelectric behavior until 2011 in the overall field of all of the people working in semiconductor materials is because having the right atomic structure is absolutely crucial to achieving this ferroelectric behavior. So the most stable phase at room temperature and pressure for hafnium oxide is monoclinic. And so this is this strict crystal structure shown here, and it's not ferroelectric. There is another phase that was heavily investigated. It's one that's often seen in thin film zirconium oxide, and that's a tetragonal phase. It has a very high theoretical dielectric constant, a big band gap, and it can also produce anti-ferroelectric-like behavior. So that looks similar to our ferroelectric plot that we plotted before, except that the hysteresis loop would be pinched in the middle, meaning that you don't have that remnant polarization that remains in the material after you take the voltage away. The structure that is really interesting for this particular application is an undiscovered orthorhombic phase, and that's the one that they first discovered in 2011. It's a metastable structure, so it's not one that you usually observe. It's only observable under certain conditions, and it's not centrosymmetric. And so because you have atoms that are displaced off of the central positions, unlike these other two structures, you actually can exhibit ferroelectric behavior in this type of structure. And so this is the one that we're aiming for if we want to make a ferroelectric hafnium oxide zirconium oxide layer. In order to do that, to get that crystal structure, we have a very wide parameter space to play with. So, there's every aspect of this very simple stack, the metal, ferroelectric metal stack that goes into making this and the processing conditions in between can really have a strong impact. So, for example, bottom electrode could induce how the ferroelectric material grows during a subsequent growth step. It could affect the crystal structure, it could affect the crystallization behavior overall. When you put the ferroelectric layer down, what temperature do you put it down at? Do you add dopants to it? What's the ratio of hafnium oxide to other materials like zirconium oxide do you use? And even once you've picked a ratio, do you apply the hafnium and zirconium oxide so they're intimately mixed, or do you separate them out into layers? All of those things can have an impact. When you put your top electrode down, you could potentially induce diffusion in between the different layers in the stack. You might get metal atoms that inject oxygen atoms that come out, and all of that can influence ferroelectricity. And then, of course, choosing the right temperature profile and the correct crystallization temperature is very important. And beyond all of these things, which we consider more process knobs to tune, we also have the electrical profile. So when we apply our electrical pulses across this material, the way in which we do that can also increase or decrease the amount of ferroelectricity that we see, and also affect the longevity of that device or its retention characteristics. So one of the things that has been observed for a long time in this field is that the top electrode and annealing strongly influence the phase. And here's an example of some films that we grew at Intermolecular. Again, so if we start with titanium nitride bottom electrode and this about 50-50 mix of hafnium and zirconium oxide, as deposited at 285 degrees C using standard amide type precursors, which are very traditional precursors used for atomic layer deposition, we actually see a very amorphous signal. So you see here that there are no peaks in this XRD pattern, and that means that there are no long-range ordered atoms in the structure. So the atoms are there, but they're mixed in a way that doesn't have any particular pattern over a great distance. If we decide to take this material and then anneal it at for 10 minutes at 500 degrees C in a nitrogen environment, we do see some distinct peaks in the X-ray diffraction patterns start to emerge. But what we can see looking at this sort of 30-degree 2 theta region is that there are several peaks present. These overlapping peaks result in this structure that you can see here. And that means that you probably have a mix of monoclinic phases as well as some of the higher K phases, most likely orthorhombic. Finally, when we cap this material with a titanium nitride layer and then anneal it, you actually see a really strong distinct peak show up right above 2 theta equals 30 degrees. And that's a classic signature that you have one of the high K phases. And by doing electrical testing, we determine that that's predominantly the orthorhombic phase in this case. So you see same material deposited on the same bottom electrode, but the order in which you do the annealing and whether you cap or not before you anneal has a strong influence on what crystal structure you get. And the bottom one here is the one that's going to be the most ferroelectric. So the goal of this study was to say, well, we really don't want that, right? We don't want a material in which it's so critically dependent on all of the structures that come before and all the structures that come afterwards. It makes the integration process of putting this into a fabrication line much more complicated. And so are there other precursors out there that could serve this purpose better? There are two precursors that are offered in the EMD performance materials portfolio. One of them is this HfD-04. Full name is bis-methylcyclopentadienyl methoxymethyl-hafnium. And so you can see the structure for that molecule over here. And then there's the analogous ZrD-04, which can be used to grow zirconium oxide. One of the interesting properties of these materials and these precursors is because they are so bulky. Compared to where amide precursors normally sit, where you run a typical growth temperature between, say, 250 and just under 300 degrees, you can actually push the deposition temperature window much higher and still achieve ALD growth with both of these precursors. And so that has some pretty interesting implications. So if you take an amide precursor, try to push it to higher temperatures, you might get decomposition of the film, which would incorporate carbon and other elements that you may not necessarily want to include. Whereas when you use the ZrD precursor, you actually get really flat growth per cycle, which indicates that you have very stable growth as a function of temperature. That's a good indication of ALD, along with some data that I'll show later. And that temperature range is now much higher. And particularly for zirconium oxide, this is interesting because if you use ZrD at these temperatures, there's a strong chance that you could actually crystallize the film as deposited. And so it's interesting to look at what phase that film deposits in to see if you get the right crystal structure. And you can see similar behavior for hafnium dioxide films grown using HfD over here, is that for the traditional amide window is down here, and then we can push that even higher all the way out to 500 degrees. And so the goal of this study was to look at the crystallization and ferroelectric properties of materials that we grow using these precursors. So now moving on to the unit films. So these are basically the films that are grown of just pure zirconium oxide and pure hafnium oxide using these precursors. We wanted to check to make sure that we had decent ALD behavior. So to do this, we used a Cambridge Nanotech 200 millimeter cross flow reactor with our ZrD-04 and HfD-04 precursors. We investigated both water and ozone processes, and you can see the other conditions that we used here in terms of dosing and bubbler temperature. These were grown typically on a silicon wafer with a native silicon oxide, and then we also investigated whether the films that we achieved changed their crystal phase substantially after we did an RTP anneal at 500 degrees C in nitrogen, as I described before. Firstly, looking at the hafnium dioxide growth rates using both water and ozone, we see a reasonable linear behavior in both of these films, and this has been confirmed on other reactors as well. The growth rates are a little bit slower than is typical for amide type precursors, but that again can be really interesting, and because these processes do take a little bit longer, they may allow for more time for the atoms to arrange themselves into different crystal structures. And so this slower growth rate may actually be interesting for the particular application that we are targeting. When we look at the crystallinity of hafnium oxide films, we see behavior that we may expect. So at 340 degrees Celsius with no anneal, basically what we see is that the thinnest film that we deposited, which is about 5 nanometers or 48 angstroms thick, doesn't have any crystallinity visible, but then the thicker films do. And so these thicker films, obvious difference being that they are grown longer in the reactor. There's also not as much force induced by the surface constraints on this material. And so this is something we observe in many systems, is that the thicker the film is, as it's grown, the more readily it crystallizes. The other thing that we can observe by examining what crystal phases these peaks correspond to is that we have a mixed monoclinic and likely orthorhombic film because we have these sort of 3 peaks that are all spread out around 2 theta equals 30. An interesting observation is when we take this material and anneal it, what you can see is that the crystal phase distribution of the thicker films doesn't change too much. And so what we know there is that whatever phase that we get when we put it down, it's actually phase stable all the way out to 500 degrees C for some amount of time. The smaller film does actually start to crystallize. You see some crystalline intensity grow here, and so that is the one that has been influenced by basically this annealing process. And then if we do the same check, but with ozone-based films, we have two thicknesses in this case, about a 50 nanometer film and something that's just shy of 100 nanometers. We see that both of these films are actually pretty amorphous as deposited, and then the thicker film does get crystalline after annealing, again in this mixed phase, as we saw before. And so this behavior is interesting, that there is an effect of which reactant gas that you use. But overall, once you do the annealing, you see similar sorts of behavior in terms of the fact that you get mixed phases with this particular material. Note that these films were grown at 300 degrees C, and so the hotter that you grow your film, it does appear that there may be a small effect in terms of how easily it crystallizes, and we have more recent data that shows that as well. Looking at ZrD-04, what we have here is, again, nice linear behavior, growth at a couple of different temperatures, and then we see a growth rate that's just under 1 angstrom per cycle in both cases. There is a little bit of a difference in terms of when you use ozone gas and you do different temperatures, you do see an increase in the growth rate, and that's something that's been observed in the literature before. But overall, these are still performing reasonably well as ALD precursors. And then this is the crystallinity as deposited for water at two different temperatures. So in this case, what we're looking at is films that were between about 4 nanometers and 17 nanometers, 18 nanometers thick. And this was done at, again, with water as the reactant at 300 degrees or 340 degrees. And we observed similar patterns. So in this case, the thinnest films tend to actually be predominantly tetragonal, meaning that they don't have a peak off to the side here or a peak off to the side here. There's just one peak in the middle. So that's encouraging, because those are the phases that could be interesting for ferroelectric or anti-ferroelectric behavior. Once these films get thicker, then you start to see that monoclinic peak emerge. And that's the case for both the 300 degree and the 340 degree films. Note that the 340 degree films are slightly thicker when we grew them, and then they also do have more monoclinic fraction present. When we look at ozone films at 300 degrees and 340 degrees, we see something really interesting in this case. So for ozone at 340, we actually see something very similar to the water case, right? So you have this one peak that surrounds 2 theta equals 30, and then these other two have monoclinic peaks that emerge when you get a thicker film. However, in the ozone case at 300 degrees C, you actually see that we can constrain the monoclinic fraction of the film down below 6% of the overall film fraction, no matter what the thickness. And so this means that for zirconium oxide in particular, with a lower deposition temperature and with ozone as the co-reactant, we're actually able to effectively suppress the monoclinic phase. And that's exactly what we want to do if we want to investigate ferroelectric or high K behavior. And so this is a really interesting finding, and one that we use to guide the deposition of films that we did later in the study. Just to show that if you anneal this film, so in this case, we're looking at the ozone deposited film at 300 before and after annealing. Most of the monoclinic fraction is still gone. And so you might have a small bit of monoclinic that emerges in one case, but in the other case, you might have a little bit more or less. So all of these kind of indicate that the material is phase stable, that it's fallen into this predominantly non-monoclinic phase, and it likes to stay there even after higher temperature annealing. So with all of that information in mind, we moved on to test the ferroelectric properties of these materials. And so the experimental conditions are very similar to what we had before. A couple of key differences is that we used an oxide substrate so that it was insulating, put a bottom electrode of titanium nitride underneath 50 angstroms deposited by a PVD. We alternated cycles between ZrO2 and HfO2 using the two precursors we talked about before, and based on what we learned, we used ozone at a deposition temperature of 300 degrees C. In the end, we applied top electrodes, which were 1,000 angstroms for electrical probing, and again, this was PVD titanium nitride. And you see the other conditions that we used for the depositions over here. How we do the ferroelectric measurement is basically a 3-part process. So first thing that we do is we check the film in its as deposited state. So we apply this triangular waveform, which is done at 250 hertz. Basically, this is cycling up to a certain voltage, down to a negative voltage, and back up again. And so as you sweep this voltage, you generate that polarization voltage plot that we talked about earlier. And the hope is if you have a ferroelectric film that you would see hysteresis. It's been observed in the literature before that applying a strong square waveform over a long period of time, in this case, we usually use a waveform that has about 3 volts on both the positive and negative side, can actually induce the material to go into an even more ferroelectric state than the as deposited state. And so we apply that kind of waveform for a total duration of 1 second at a 1 kilohertz rate, and so you get basically 1,000 cycles of this plus and minus 3 volt pulse. And then we do the hysteresis with the triangular waveform again to try and investigate the polarization voltage plot before and after applying this electrical stress. So we did physical characterization of this material first, and as expected, using these particular growth conditions, we were actually able to substantially suppress the monoclinic phase of this film, constraining it to no more than 20% of the crystalline fraction of the material. And interestingly, even though we didn't anneal this film at all, we were able to get very strong ferroelectric performance. So here are the polarization field plots for pre-stress and post-stress for a device that's made using this stack. And overall, we see that we get, after stress, especially a 2PR, which is the overall size of this loop opening of around 27 microcoulombs per centimeter squared. So we have both the phase suppression and the accompanying ferroelectricity in this material, even without applying any special protocol to cap and anneal this film after deposition. And so this is really different than the behavior that we see with the amide precursors that we showed at the very beginning of the presentation, because in that case, you only got the phase that you wanted under certain specific conditions, whereas in this case, presumably because these films are phase stable and because we can apply the top electrode and not have to perform any specific annealing in order to get this film to crystallize in the right phase, you could actually have much more independence about what electrodes you choose, what thermal profiles you choose, and this could be very beneficial overall to the field of depositing ferroelectrics for a variety of different applications. So to summarize, HfD-04, HfD-04, and ZrD-04 show linear ALD growth with both water and ozone. And particularly for ZrO2 grown using ZrD-04, there's strong monoclinic suppression with ozone at 300 degrees Celsius. That extends results from the paper that I show here, which investigated some of the properties of these films before. And hafnium oxide films are amorphous as deposited at 300 degrees Celsius. And when you combine these two films, HfO2 and ZrO2, in alternating cycles using the precursors we talked about, then we produce a crystalline film as deposited with strong ferroelectricity. And so that concludes my presentation for today. If you'd like to reach me, here's my email address, and I'd be really happy to take any questions that you have by email and connect with you on LinkedIn. Thanks again for listening, and we'll talk to you again soon. Bye.